start recording. Could someone say something quickly just so I can check if the audio is in the recording?
Hello, Adam.
Yes, we're good. Yep, all good, all good. Thank you for all the all goods in the chat. And I will switch my camera to this one. Hello, guys. Think you can see me now, hopefully?
Yeah.
Yes? Okay, good, good. And the screen, obviously. That's an important thing, too, to see. Um, before we begin, welcome to the live stream. If you don't, if you're joining from SYE, then you probably already know about my notes. But if you're joining from somewhere else, then you can always find my notes at www.tutor.ca/notes. So I write notes for all of the courses that I take. Oops, that's not what I meant. Well, that's actually the website, but didn't mean to launch it. And then you can take a look at my notes here. So of course we have I have notes for discrete math, which I updated today. So today I just if you download it today, I just added a conclusion and I fixed some typos that were in there. I just read it through. Feel free to go download that. You can go to this website for my notes. And today I have some questions planned for us. How many questions? I don't remember. Oops. Let's do a quick count. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have like 20 questions maybe for us. I don't know if we're going to be able to get through all of them, but I'll go through a couple. And let's just see if we can understand everything that's going on. And if you want, I can post like the rest of the questions that I was going to do after if you want to try them out. I collected some questions from different textbooks and different online resources and stuff like that. A lot of the questions are from this time are actually from Benato's textbook, like the course textbook, but a lot of them aren't as well. I have different ones. But anyways, I just thought I'd go through some in detail. Okay, so I will get going. Let me see if my tablet works properly. It does. Any last minute things I should do? I should drink some water before I start talking. Okay, so in general, the course after the midterm, the course after the last test includes this content. No, let me just no color it. No color. There we go. So we start with the Euclidean algorithm, which is kind of connected to linear Diophantine equations, right? So we're going to start talking about that kind of as a group. Then we have congruences, congruence classes, and congruence inverses, right? These are just a separate topic about congruences, which kind of all go together. And you use linear Diophantine equations to solve congruence inverses. And then we have the whole combinatorics section, right? So sum rule, principle of inclusion-exclusion, product rule, pigeonhole principle, combinations, and binomial powers at the end. So we'll see how many we get through. If you guys in the chat, let me know, what do you think is the thing you want me to, like you specifically want me to do from this list here? Is there any like specific ones that you're like, oh, I want you to do, focus on this extra question here, try, because I have a lot of questions. I don't know if I'm going to be able to get through all of them. So if there's any particular ones that you want me to do, make sure you say them now. Yeah, congruences and linear Diophantine equations. Yep, for sure. Anything else? Modular inverses. Yep. Congruences. Yep. Sounds good. So it looks like mostly congruences. Anything else? Proof questions? What kind of proof? Proof by induction? Or wrong course? Wrong course. Inverses, yeah, for sure. That sounds good. Yes, this is for sure recording. I should have said that. Yeah, this is definitely recording. This is, and it'll be available on my channel. You can find my channel by going to this link, or just look it up. My name. Just search YouTube. Adam. Right there you go. Not Gianluca. That's the name, but it's okay. Yeah, what is principle inclusion exclusion? That's principle of inclusion exclusion. That's what that is. Yeah. I think someone's got their microphone on. Who's got their microphone on? Ethan Zelmer, my friend. You got your microphone on.
Whoopsies. Thank you very much.
No problem. No problem. Okay. So sounds good. We'll start with Euclidean algorithm, and then we'll move on to linear Diophantine. We'll just kind of do it in this order because I'll do one example of Euclidean algorithm, although we've done lots of them. I don't have to do the whole example for that. The first example is use the Euclidean algorithm. So use the Euclidean algorithm. I'll probably misspell Euclidean every single time. Use the Euclidean algorithm to solve. And what do you want to solve? You want to solve the greatest common divisor of 44 and 17. 44 and 17. Okay, so we will do this in the way that you should do it because it's useful for linear Diophantine equations, right? There's a way to do it like that. There's a kind of a simpler way to do it if you're just talking about greatest common divisors, but we'll do it this way. So essentially what you do is you say, okay, well, I mean, this number here is smaller than 44, and if it wasn't, you could just flip it. And we just say that, okay, this number is made up of some amount of this plus some remainder, right? So 44 is made up of some amount of 17s, I don't know how many, plus something, right? So you can do this just by eyeballing it, or you can also do it by, some sort of calculator trick that, Bonato has taught. So reliably, you can just do the bigger number, divided by 17, right? And so I get 2.44. I'm not going to do this whole explanation every time, just for right now. So this gets, 2.58823 ... right? So you just take this 2, and the 2 goes over here, right? So it's 2 of 17s plus some remainder, and the remainder is this part here, right? So if you just take that remainder, right, and you multiply that by 17, you get the sort of you get the actual remainder that's written in here, right? So this is going to be plus 10 here. And it should be true that 17 times 2 is 34 plus 10 is 44. So we have this here. And you're just going to do this over and over and over again, right? So I'm just going to, kind of represent that, this line represents the greatest common divisor of 44 and 17. And you kind of keep doing this. Yeah, it is just like mod. Yeah. You definitely use remainders and stuff like that all the time, right? Also in congruences. And then you do the same thing, but for the next one, you say, now, okay, I can make 17 from some 10 plus something times 10 plus something. So this one's a little bit more clear, 1 times 10 plus 7, right? And this kind of represents the greatest common divisor of 17 and 10. 17 and 10? Yeah, 17. Which is going to be the same thing, right? That's kind of the whole point of the theorem, is that this greatest common divisor is going to be the same as this greatest common divisor, right? And then we can keep going. We can say, okay, well then 10 is equal to 1 times 7 plus 3, right? So if I just draw some arrows here to help, that moves like that moves like that moves like that, right? So then next one, we have 7 is equal to 2 times 3 plus 1, right? We have this. And then finally, we have 3 is equal to 2 times 1 plus 1. Yeah, is that right? That is right. Okay. Yeah, okay. I move the 1. I move the 1 here. Move the 3 there. Move the 1 there. Yeah, that's fine. And then there's just going to be one more. So 2 equals 2 times 1 plus 0. Okay, and so you end here, and this is your greatest common divisor. That is your GCD, right, of the original thing. Where have we got the 3s? 1.7 plus 17. Oh, plus 3. Yeah. Well, one time, just because you can do this just by. I can't. Minus 0. Are you? I can't tell if you're correcting me or you guys are correcting me or you're.
No, I was saying that. Like I think most of us. Like, so I think you did the 3 equal 2 times 1. I think most of us did 1 times, like 3 times 1, and then remainder 0. So you did an extra step in that sense.
Okay. Yeah, I see what you mean. Yeah. 3 equals 2 times 1 plus 1. Just do 3 equals 3 times 1 plus 0.
Yeah. You get the same remainder of 1.
So okay.
GCD of 1, yeah.
I guess so. Yeah, you get the same thing. It's just that this matches the pattern better though, right? Because you just have the arrows, like this just moves down, so you just keep moving that down, right? That's the reason I did like that. I see what you mean though, that would be the same thing, right? Because then here this is going to be 2 times 1, and the 2 moves. Oh no, and then okay, whatever. It's the same number. Okay, GCD of 44 and 17 is going to be 1 there. Okay. So we can see that that's true now, right? I guess it also helps to say that if you do it this way, wouldn't it be 1 plus 1 equals 1 times 1 plus 0 at the end? If you do it my way? Yeah, I guess it should be 1. Yeah, that does make sense actually what you're saying. It should be 1 equals here. Again, it doesn't really change the answer, but 1 equals 1 times 1 plus 0. Yeah, that does make sense. And that's probably, we should leave it like that. That wouldn't affect really anything, but yeah, that makes more sense what you're saying. So move that down. There's our GCD, and we did it using the Euclidean algorithm. So there you go. That's that. Okay, let's take a look at another example. That's all I'll do of just using the Euclidean algorithm. But of course, lots and lots of questions that come after this will use the Euclidean algorithm, right? It's kind of a big thing that we do in this part of the course. So we'll just keep doing it, including here. So 5.23 from the homework showed that there's no integer solutions to this. Of course, we know how, but let's just write it out. So there are integer solutions if the greatest common divisor of 2173 and 2491 divides 210, right? This is the condition. So if this is true, then the LDE has solutions, right? And this isn't all going to go to waste because the next question has the same GCD, so we'll just use that. So anyways, you'll see. So we got to find this GCD now, right? So that's what we're trying to find. GCD of 2173 and 2491, right? So we start again with, the big number 2491 equals 2173, or 1 times 2173, right? Plus something. I don't know. Let's see what. 2491 minus 2173. 318. Okay, I'll try to go slowly, make sure I don't make any mistakes, but if I do, feel free to stop me. So 2173 equals something times 318 plus something. So we got to figure that out. So I'm going to do 2173 divided by 318 is going to be 6 point something. So I'm going to have 6 times 318. And then I have a huge remainder, so I'm just going to multiply that by 318, just the remainder. And I get 265. 265. Okay, then I do it again. So you just keep going until you have a remainder of 0. So you just have, now 318 is 1 times 265 plus something. So just, you keep seeing those arrows moving from right to left. So 318 minus 265 is 53, right? We keep going. 265 equals something times 53 plus something. So 265 divided by 53 is 5 exactly, right? So we get 5 times 53 plus 0, right? So 53 is our GCD, right? GCD is of 2173 2491 is 53, and 53 does not divide 218, right? So if we just try it, right? 210 divided by 53 is not a whole number, so there are no solutions to this one. That's all you have to do. Then for the next question, it's pretty much the same thing. It's just that it says find all integer solutions to the pretty much the exact same LDE, but this time it's equal to 53 instead of equal to 210. So the first part of this would be exactly the same, right? So let me just let me just copy this down. The first part of this is exactly the same as the last part. Whoops. That's not what I'm meant to do. But this time, our GCD will actually divide that number, right? It will actually divide. So let me just paste this. It does not like, OneNote does not like when I try to copy and paste things for some reason. Oh, sorry. Wow, okay. Yeah, OneNote is not happy with me at the moment. Let's see why. Oh, there we go. And we are back. Okay, let me try to paste this. No, not happy with me. Okay, let me just try this again. I think it's bugging the software. Yeah. OneNote has problems. Okay, so same thing. We want to just check if this GCD divides 53. So yes, 53 does divide 53, and so this does have solutions. And we're going to use these numbers to figure out what those solutions are. So the way we do this is we kind of use all these equations, right? So I'll say A, B, and C. We use these equations to kind of backtrack, right? And then we try to get an equation in this form, because once we have a particular solution, we can find all the solutions after. But I'll explain that in a second. I have a question in the chat. If such a question, do we assume that it has a solution, or do we prove it first? You you need to find the GCD anyways, right? So no, you don't have to assume that it has a solution. You can just prove it first, but proving it is just finding the GCD, which you need again, right? You need to find the GCD anyways. So it doesn't really, yeah. Does that make sense? Hopefully. Joshua, you have a question?
Yeah. So when we do something like this and find all integers x and y, is it like many? I don't remember how many.
Yeah.
It's like
Yeah.
infinite, or that there's a set amount.
Yeah, no, it's infinite. So it's an LDE either has one solution. Oh, sorry, either has no solutions or infinite solutions. Right?
Okay.
And what you need is to figure out the infinite solutions. You just need to find a particular solution, and then you can kind of like branch off of them to find all the rest of them. So what that kind of looks like, if I go to my notes here, you can see what I mean. Let me just open the notes here. 314, this one. So if I scroll to, just find it here, linear differential equations, there we go. So if you find a particular solution to linear differential equation, can you see that? Hopefully my camera's not covering that.
Yeah, it's good.
Yeah. So this is, any x, any y. It's made up of a particular x and y, right? Particular solution. You have to find someone. And then you find all the rest of them by just adding or subtracting this fraction, right? So here it's b over the GCD. Here it's a over the GCD times t, times some integer. And you can find all the infinite solutions by just varying this t. Does that make sense, what I'm saying here? Hopefully. Yeah, okay, good.
I just want to see the question. So funny.
Okay, good. Yeah, so we're gonna do that in this one, but first we have to find this particular solution. Right. Okay, so let's continue. I need to find the particular solution now. So the way I'll do that is I need an equation in this form. I need 217 times something plus 2173 times something plus 2491 times something equals 53. So I'm going to kind of backtrack here because I have these numbers, right? I have these numbers. They're kind of way up here. So if I just keep back substituting, right, I'm going to get an equation in this form, right? So what I'm going to do is I'm first going to take this C value, right? I'm first going to take a C equation, right? And I'm just going to rearrange it for 53. Okay, so it's going to be 53 equals 318 minus 1 times 265. Right? Okay, we have this, right? Remember, it's important that I have this form after, so we shouldn't actually start multiplying things out here, right? We shouldn't actually start multiplying 6 times this, right? We want to have actually these numbers visible so we can find the solutions. Kind of pattern match. So we don't want to multiply anything out here, but you do want to distribute when you have an option. So I'll show that in the next step. Here, we want, so we have this, we rearrange this equation. Now we're going to take B, right? We're going to take B, I'll move it here. I'm going to rearrange B. B is going to turn into 265 is equal to 2,173 minus 6 times 318, right? And I'm going to substitute this in for 265 here. And the reason I do this is because, look, I'm introducing 2,173. Remember, I want 53 equals, backwards, but 53 equals something with 2,173 and something with 2,491. So I'm going to get the 2,173 in here. And then when I rearrange this one, or substitute into this one, I'll get the 2,491 as well. So let's just do that. So I'll number the steps here. So this was step 1, step 2, step 3, right? So this is kind of still step 3. So I get 53 equals 318 minus 1 times 2,173 minus 6 times 318. I just substitute in 265. I might have said 256 before. I meant 265. Then we have 53 is 318 minus, so distribute now, right? So minus 1 times 2,173. And then, okay, I'll just say plus 6 times 318. Right? And then you can collect like terms. Like we have like terms. Remember, you want to kind of treat the numbers like a variable here. So it's going to be, I'll just call 7 times 318 minus 1 times 2173. So kind of going from like here to here is like a step 4, right? Kind of just distributing and collecting like terms there. And we're almost there, right? I'm like, this equation is kind of in the form of our original one. I just have to deal with this first one. So what I'm going to do is I'm going to take A now, right? And I'm going to take A and I'm going to rearrange it for 318, right? So I'll just do it over here. This is kind of our step number 5, I guess, right? And I'm going to rearrange. So 318 is 2,491 minus 1 times 2,173. Then I'm going to substitute that in, right? I have an expression for 318 in terms of these numbers that I want. I want those numbers, right? They're on my left side of my LDE. So I'm going to substitute that in here. So it's 53 is 7 times all this. Minus 1 times 2,173. So I'll just a little arrow kind of connecting this. A lot of arrows, but hopefully the numbering helps make sense of it. And then we distribute. So 53 is 7 times 2491 minus 7 times 2173 minus 1 times 2173. So collecting like terms, we get 53 is equal to, yeah, so I'll move the 2173 to the front. So it's negative 8 times 2173. And then plus 7 times 2,491. Yeah. And that should be fine. 21, 8, and 7. Yeah, that's fine. Okay, and so notice that this is exactly the form of our equation, right? Okay, it was backwards, but let's just put equals 53, right? It's exactly the form of our equation here. So the solution for x is negative 8, and the solution for y is 7. And that is our particular solution to the Diophantine equation, right? So we have x naught and y naught equal to negative 8 and 7, respectively. Remember our GCD of 2173 and 2491 was equal to 53. So now, to get the actual full solution, we use this kind of formula, right? We use this formula here. We say, okay, so it's any x value, which is a solution to this, will be written in the form negative 8, right? Plus b, the way it's good to remember it is like the x solution gets the other one, right? So it's going to be 2491, right? The x solution gets 2491 over the GCD. The GCD was 53 times t. And then the y is the y naught, which is 7, minus the other one. So 2173, so not the y term, right? The x term. Minus 2173 over 53 times t for any t in the natural numbers. Or actually, it has to be natural numbers. Yeah. Or it can be integers too. Yeah, it can be integers too. So tz. There we go. Did I put that here? Yeah, tz. Okay. And there's your full solution. You can divide these numbers, but so 2491 divided by 53 is 47. Okay, it's 47. And then 2173 over 53 is 41. Does that match the solution? It does. Okay, and so any expression in this form is a solution to this LDE here, right? So if you wanted to find like one of the solutions, so let's just say solution number 1. Let's say when t equals 0, right? When t equals 0, x is negative 8, y is 7. That's a solution. That's the particular solution we found. But you could find another solution. You could say, okay, solution number 2 is when t equals 1, right? And so then x would be negative 8 plus 47, and y would be, t is in z. Yeah, exactly. And then y would be 7 minus 41. And those are some numbers. And that's also a solution to this. And that's all. Yeah, t is element of z. That's a horrible z there. Let me try to write that a little nicer. There we go. I struggle with the second line of the z. There we go. Okay, that's a little bit better. A little bit less chicken scratch. Okay. There's our first full LDE equation done. How do you guys feel about this?
Yeah. Could you just the backtracking always the backtracking is confusing me sometimes. It's just
Mhm.
like, all right, you started with the 53 equation, and then you went back from there.
Yeah, I started with this equation because remember our LDE is equal to 53. So I want definitely to say, to say equals 53 here. Now there's some examples where you don't do this, but you want to say equal to 53. You always start though with the last equation before the 0 one. You never use this one. Right? You never use this one. So you
Which
always
one?
start. You never use this one.
Oh, the one at 0. Okay.
The 1 plus 0, right? So you always start with this one,
Mhm.
and you isolate for this variable here, right? You just always isolate for this one. You always isolate for this one, and just keep back substituting. You always isolate for the remainder, and then just keep back substituting. So you see, we isolated for the remainder here. Then in step 2, I took my equation B, isolated for the remainder, 265 equals, right? I got that
Yeah.
alone. And then I substitute 265 into this original equation here, right? Because there's 265 there. Simplified a little bit. Then I went back up to part A, to equation A, isolated for the remainder, 318. And substitute that into here, because you see there's a 318 there.
Yeah.
And then just simplified, kept simplifying, right? So honestly, with this kind of stuff, it's you just have to like look through it and try to like each individual step is not super crazy, but it's just a wall of numbers, right? So it's intimidating to look at. So just try to like identify what I'm doing between each line here, right? And that's a good way to try to practice this kind of stuff. And then the whole point though is at the end we have an expression which is in this form, the form of the LDE. That's the whole point.
Okay. And earlier you said something about the x equation taking the b value, so 249. Okay.
Yeah, exactly, right? The x equation takes 2491, the y value, like the not the y value, but the coefficient on the y, and then the y equation takes the coefficient on the x, just flipped.
Yeah.
And that's it. Okay, so any other questions for this one? Can move on otherwise. The next one's a little bit trickier. Has a negative sign in it. So here we actually do pretty much the same thing. Right? Nothing actually changes that much, but what you want to do here, so it's solve the linear Diophantine equation. You say, okay, we have this. So when you find the GCD, just keep it positive. Okay, 7 and 9. Just keep everything positive when you're finding the GCD, and then account for that negative sign when you're actually assigning a particular solution. That's what it is. So just keep it positive. So 9 is equal to 1 times 7 plus 2. 7 is equal to 3 times 2 plus 1. And then 2 is equal to 1 times 2 times 1 plus 0. Okay. So GCD is 1 of 7 and 9 equals 1. 1 definitely divides 3, right? 1 divides 3. Let's make a bigger line. 1 divides 3. So this has solutions. So we can do that much. And we just backtrack now, right? We do the same thing like before. So we start with this equation. It's really going to be a quick backtracking. So we start with this equation, right? We take it down here. I isolate for 1 this time, right? So 1 equals 7 minus 3 times 2, right? Then I take this equation. So that was step 1. Then I take this equation, right? Or maybe I'll do it over here, I guess. Take this equation. And I isolate for the remainder. Always you just isolate for the remainder. So 2 equals 9 minus 1 times 7. And then what I'm going to do is I'm going to substitute this equation in. So 1 equals 7 minus 3 times. Now, instead of 2, I'm going to say 9 minus 1 times 7. So I get 1 equals 7 minus 3 times 9 plus 3 times 7. So I get 1 equals 4 times 7 minus 3 times 9. Is that the solution? Yeah, there you go. So if we compare it to our linear Diophantine equation, we're not quite there yet, right? So first of all, it's not equal to 3. That's an issue. But we can fix that relatively easily just by multiplying by 3, right? So I'll just say times 3. So it's going to be 3 equals 12 times 7 minus 9 times 9, right? And now, okay, I just moved the equals 3 to the other side. Now we are in this form. And so you just have to be very careful with how you're assigning x naught and y naught, right? So x naught is 12. Y naught is 9. Or, yeah, it doesn't really matter how you choose it. But anyways, 9. Yeah, positive 9, not negative 9. Because the negative is part of the equation, right? It's part of the equation. Just keep it positive, exactly. That's what you gotta do. So, I like that. So here you see that y naught is just going to be a positive 9, not a negative 9. So that's an important distinction there. The negative is part of the actual LDE itself, not part of the solution. So you have that there. Okay, there is that. Then to find the what did we say the what did we say the GCD was? GCD was 1, right? So then to find the actual particular solution, sorry, that's the particular solution. To find the general solution, you do the particular solution plus, so the other term, which is negative 9. So here you include the negative. Let me just make sure I know what I'm saying. Yep, here you include the negative, so it's really going to be minus 9t, 9 over 1t. And then y is equal to y naught, 9, minus 7 over 1, right? T. And you get that. And we can get rid of the over 1s, doesn't really matter. And we have this here. And that's correct.
Wait, was the formula, does it have a negative sign, or is it because of this
Yeah,
particular
no,
solution?
it's the formula has a negative sign. Where's the formula? Here. The formula has a negative sign. Right there.
Yeah. Okay, so how is both of them negative just now? Or did I see that wrong?
Yeah, no, it's so here it's positive, but then the value is negative 9. The value is negative 9 that you're putting, because for the extra you put the opposite one, so negative 9 goes there. So the plus and minus turns into just minus.
Oh, yeah.
And then here it's just minus 7. Minus 7. Does that make sense?
It's negative, yeah, it's negative and then A, right?
Mm-hmm. Negative A,
Okay.
so negative 7.
Over GCD of AB, okay.
Mm-hmm.
Makes sense.
Exactly, yeah. That's it. Okay, so, yep, that's it. If anybody is following along with the textbook, you might notice that the textbook has a different answer, but it's the same answer. Like it's my answer is the same answer. It's just slightly written differently. So the textbook's answer is x equals 3 minus 9t. And is that right? Yeah. And y equals 2 minus 7t. So you know how this happened, right? It doesn't really matter because notice this is the same, right? And this is just a different particular solution. It doesn't matter which particular solution you use. It's just a different one. So notice that if I set t equal to 1, I get this particular solution. T equal to 1 would be 12 minus 9 is 3, and 9 minus 7 is 2. So it's just a different particular solution. I don't really know why he did like that. I mean, this is definitely the particular solution you'd get if you did it the way instructed, like it's instructed to, but doesn't matter. In case anybody maybe watching this later notices that the textbook solution is different, it's the same thing. Okay.
Wait, I'm confused about the textbook, actually. Now that you introduced it, I'm confused as why it would have that. Can you explain again? So
I don't know how he got this solution, but it is the same thing as this solution.
Because if we solved it, we'd get x naught and y naught to be 12 and 9, right?
Yeah.
So then where do these values come from?
I don't know. That's what he wrote. But it's also it is also a particular solution. So it's fine. It's correct. Just as correct as mine. But it's just a different particular solution used here for whatever reason. Maybe he did yeah, he might have done it by inspection, or maybe he like just typed it into like Wolfram Alpha, and then Wolfram Alpha like, gave that, right? Which is fine. Like he doesn't have to solve every question. But like, yeah, maybe he just typed into Wolfram Alpha and that's what spat out. It's fine. And now we're here talking about it all because Wolfram Alpha is gives a different particular solution. Anyways, let's move on. That is all the LDE, just like straight do an LDE equation that I had. Now I have some other ones that are related to inverse, so we'll do another one there. For now, I think, let me check off what we've completed on my screen up here. So we have completed this one, those three, Okay. I'm ready to move on to congruences. Are you guys ready to move on to congruences?
Can you check off what we did exactly? So we did Euclidean algorithm and
Oh, like from the top here?
Yeah.
From the top? Yeah. Well, we've done these two.
Okay. Cool.
Give it a so yeah, so we'll move on to congruences now, if that's good with everybody. So the congruence question I have is yeah, we can start with this, I guess. That's fine. We can start with this one. 5.7 from the textbook. I promise I have other questions that are not congruence questions. I mean, that are not questions from the textbook. A little bit later for the other stuff. Most of the questions here are from the textbook. So find the smallest non-negative integer x satisfying the following congruence equations. So here, right, we're trying to figure out what is 491 congruent to x, congruent to mod 17. So let's talk about congruences for a second here, right? Congruences. It's kind of a way to say that, like, two numbers are the same, right, relative to some multiple, right? So for example, the example that I put in the book here is the numbers mod 12, right? The number is mod 12. So you can always think of congruences like a wheel here, right? It's always good to think about it like that. So, like mod 12, right? You're pretty much just asking how far off from a multiple of 12 are you? That's all that means. So I have it here, right? If A is congruent to B mod n, that means that A is B above a multiple of n. So for example, 12 is congruent to, I don't know, 2 mod 10, right? Mod 10. Mod 10. Right? Because it's 2 above, so 12 is 2 above a multiple of 10. But so is 22, is also congruent to 2 mod 10. And so we can kind of say that, 22 and 2 are the same mod 10. Or if you think about it in terms of, mod 12 here, right? We have every number kind of fits into a category. Every number is either going to be congruent to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, mod 12. So this is kind of like the mod 12 circle here. Very surprised he didn't include this in the lecture. I think the circle is a great way to learn about congruences, because you see every number fits here. So 0 is congruent to 0 mod 12, right? It's part of this thing here. And I'll just give you a hint, all of these kind of represent congruence classes, right? But we'll talk about that in a second. So 12 is also congruent to 0 mod 12. Both of those are congruent to 0 because 0 is 0 off of a multiple of 12. 0 is a multiple of 12. 12 is a multiple of 12, so it's 0 away from a multiple of 12. Same with 24. So these are kind of all the multiples of 12. Multiples of 12 are same thing as 0, right? Mod 12, right? Because mod 12 is talking about multiples of 12. And then all of these guys are numbers that are just one above a multiple of 12. And there's an infinite list, right? And the next ones are all the numbers that are 2 above a multiple of 12, all the ones that are 3 above a multiple of 12, 4, 5, 6, 7, 8, 9, 10. And then when you're 11 numbers above a multiple of 12, right? If you go one more, you're not 12 above a multiple of 12. You're just 0 above a multiple of 12. Right? That's a lot of words I'm saying, but being 12 places above a multiple of 12 is exactly the same thing as being 0 places above a multiple of 12, right? And this is true generally, of course. So being n places above a multiple of n is the same thing as being 0 places above a multiple of n, right? Because if you're 12 places above a multiple of 12, you're just on the next multiple of 12. So it repeats, right? So every number is kind of contained in the cycle. Every single number is contained within the cycle. Of course, you can keep going, right? 35, 36 would be here, 37, 38, 39, right? It keeps going like that. And so every number fits into one of these little slices of the wheel, and each one is a congruence class, right? So you can kind of think of it like that, but that's when you think about it as an equivalence relation. But the general idea here is that mod n, every number fits into one of the n slices, right? One of the n slices. That was a quiz question, is if you have a, if it was like mod 19 or something like that, how many congruence classes? Well, there's 19 because there's 0 to 18. Right? So here we have 12, we have 0 to 11, that's 12 congruence classes. And yeah, there we go. So hopefully that makes sense a little bit as an introduction to like what congruence is. I mean, hopefully it's not an introduction because obviously we've had this for a while, but if it's like a good way to look at it, because a lot of people don't, I don't know, notice it like this. But yeah, okay. So now we know a little bit. I introduced congruences, with the wheel, which is a good way to do it. Again, this is a great way to think about congruences. This is like how you can just get it instantly in your head. You don't have to do this whole, formula. Of course, there is an actual formal formula for congruences. So here's the formal definition. But this one works just as well, right? So for example, here, it's defined within division, right? So that means that, this should be an n. Oops, didn't catch that. This should be an n. This should be an n. So n divides the difference, right? Is another way to think about that. So yeah, there we go. So okay, we have this now. That is the congruences. We can move on to this question. We can actually answer this question here. So to answer this question, we just want to figure out, how far off is 491 from a multiple of 17, right? So what we can do is we can just try to figure out what multiple of 17 we're closest to, right? So you can write 491 as something times 17 plus something. And this something will be that congruence, right? Because that's how far off you are from a multiple of 17. So 491 divided by 17 is 28 point a bunch of stuff, right? So if you just take the decimal, multiply by 17, we get 50. So it's 15 off of a multiple of 17, and so 491 is congruent to 15 mod 17 for part A, right? And that 15 comes from this number here. It's how far off we are from a multiple of 17. Make sure I got that right. To get that right, that's fine. Okay. Of course, if I'm going too fast or something, want me to explain something again, feel free to let me know. Happy to answer. But yeah. Next one, 55. It's congruent to what mod 4? So again, we just want to figure out how far off is 55 from a multiple of 4. So 55 can be written as something times 4 plus something, right? That's what we could. Can I remember what multiples of 4 is? So it's probably going to be 3. I think it's 3. Let's. Can we just do a over n minus the whole number of times n? Yeah, that's exactly what I'm doing. Yeah. So a over n, right, is 55 divided by 4, right, is going to be 13 point something, right? And then I just take that point something, 0.75, and multiply it by 4. And so it's 3. Yes. My mental math did work there. So we have 3 mod n, mod 4. So 55 is congruent to 3. So 55 is the same as 3 mod 4. Now, the same as is not a very formal thing, but that's kind of like what we're kind of saying here, right? It belongs to the same slice of the circle. Okay. The negative ones are not that bad either, right? So let's check here. Yeah. So for part C, we have negative 1,999 is congruent to something mod 10, right? So again, how far off is negative 1,999 from a multiple of 10, right? Well, it's 1 above a multiple of 10. Does that make sense? I mean, I'll do the actual math for it as well, but it's definitely congruent to 1. Because it's 1, a multiple of 10 is negative 2,000. That's a multiple of 10. So this is 1 above it. So it would be congruent to 1 there. Does that make sense? I'll do the actual math here too. So we can write negative 1,999 is equal to, something times 10. I don't think I ever tried it like this, so let's see if it works. Something times 10 plus something. The negative sign might screw us up. What happens? Let's do negative 1,999 divided by 10. Oops, divided by 10. So we get negative 199, right? So I'm going to subtract off. That doesn't make sense. Yeah, I just need the decimal. So just 0.9 times 10, and that's 9. So plus 9. That doesn't quite seem right. No, I must have to add negative 9 here.
Would it be like
Yeah.
negative
So actually,
9.
being congruent to negative 9 is actually right too, right? So negative 1999 is congruent to negative 9 mod 10. That's fine. That is true. And how do I know this? Well, the negative works. Like, this rule works the same. If it's negative, that means you're 9 below a multiple of 10. That's true. It is 9 below a multiple of 10. A multiple of 10 is negative 1990, and it is 9. This is 9 below a multiple of 10. So it is congruent to negative 9. But you'd probably want it to be, the mod answer can't be negative, so like he wouldn't accept it as negative. Yeah, I mean, it is still mathematically true. The question didn't say, oh, sorry, smallest non-negative integer. It does say smallest non-negative integer. You're right. That's fine though. So the calculator trick doesn't get you the wrong thing. But you do just have to account for it now, right? So it's just really good to think about it like this. If you just think about congruences like this, you can deal with it, right? So being 9 below a multiple of 10 is the same thing as being 1 above a multiple of 10, right? So you would just jump right to this. You can just jump to this thing. All right, so again, think about it, right? Being 1, if you think about it like this negative 9 means that negative 1999 is 9 below a multiple of 10, which is the same thing as being 1 above a multiple of 10. So if you're at a multiple of 10, right, you go down 9 places, then you are certainly 1 above a multiple of 10. And the end. Okay, so that's part C. And then for part D, you have negative 177 is congruent to x mod 3. Mod 3. So here we have the same problem. We just need to figure out, how far off is negative 177 from a multiple of 3. So let's figure it out. I don't know. I guess I'll do it like this. Negative 177 equals something times 3. So negative 177 divided by 3 is negative 59 times 3 plus, and then, oh, that's it. It's negative 59 times 3. So that means there's no remainder, right? Plus 0. So negative 177 is congruent to 0 mod 3. There's no remainder. So there's nothing to do. It is a multiple of 3. Negative 177 is a multiple of 3. So it's just congruent to 0. Okay.
So
yeah.
So technically, with the negative questions, if you find a remainder, you just kind of flip it. So if you have mod 3 and you got if you had mod 10 and you got negative 9, it would just be 1.
Yeah.
And so on.
Yeah. That's it.
Yes.
Yeah, that's correct.
But if it's positive or negative, if you get 0, it's just 0.
It's just 0 because it's a multiple of 3. It's just a multiple of 3. Exactly, yeah. That's it. Okay. So, any questions about this? Otherwise, I'll move on to more modulus questions. But any other questions here with this one? Okay. I will carry on. What would be the case for negative 177 x mod is congruent to x mod 4? Let's see. Part E, let's say. Negative 177 is congruent to x mod 4. Okay, so, well, I'll divide it by 4. So, negative 177 is equal to negative 44 times 4 plus, and then my negative 1. Negative 1 here, right? So it is 1 below a multiple of 4, right? So negative 177 is congruent to negative 1 mod 4 because there's a multiple of 4 and it's 1 below it. So being 1 below a multiple of 4 is the same thing as being 3 above a multiple of 4. So you do 177 is congruent to 3 mod 4. Right? And that's it. Yeah, it's 3 above a multiple of 4. Okay, good. So yeah, that's a good question. Thank you for suggesting that. So let's take a look at the next one. 5.10 is find the least non-negative integer x such that 17 to the 213 x is congruent to x mod 15. Use the fact that whatever. Use some factor. Okay. So these are tricky questions, right? These are pretty tricky. But we're going to use a very important property about congruences, which is this one right here. This one. Right? So if we have that A is congruent to B mod n and C is congruent to D mod n, then you can kind of multiply those equations together, right? And you have that AC, multiplying these two, right? Right? AC is congruent to BD mod n. And so what we're going to end up doing is we want to write 17 to the 213 as a long product of things that we can find its congruency to n, to 5, I guess, in this case. And then multiply all those congruencies together, like the x's together. So first of all, the way you do this is you write this as a bunch of powers of 2. You write 213 as a bunch of powers of 2. So I have to remember how to do this. I mean, not how to do this, but I have to just like take a second. So 2 to the 5 is 32, to the 6 is 64, to the 7 is 128. So 2 to the 8 is going to be too big. Yeah, 2 to the 6. So it's going to be 2 to the 7. 2 to the 7 is 128. So is 128, 2 to the 7, plus 64, 128 plus 64, yeah, is 192. So plus 64. So this is 192 now. Do I know why I break into powers of 2 instead of any other number? Yeah, why do you break into powers of 2 instead of any other number? Could you do any other number? I think you could. Yeah, I think the reason you do 2 is just because it keeps the numbers the smallest, especially because we're going to keep squaring things because it's 2. We're going to keep squaring you'll see in a second, we're going to keep squaring exponents. So multiplying by 2 keeps numbers smaller than multiplying by 3 or something like that, but I think it would be the same as multiplying by 3. I know for a fact that every number has a binary decomposition. I don't know for a fact that every number has like a tertiary, like to the power of 3, or like a base of 3. No, it does. Never mind. So then yeah, I think it's fine if to do any other number, but this is how it's taught to us to do it like this. It's the same. You don't use base 2. Yeah. Okay. Yes. Thank you, Caleb. I will do that. So 2. This is 2 to the 6, and then we're saying not plus 32. Plus 32 would be 288. Okay. Let's just follow. Is that what I have here too? 2 to the 128, 64, 16, 4, and 1. Yeah. Okay. That's fine. Plus 16 plus 4 plus 1. That's 2 to the 4 plus 2 to the 2 plus 2 to the 2. Right? Smaller increments make it easier to get desired value. That is true, for sure. Okay. So we know that 17 is equal to 17 to the 128 times 17 to the 64 times 17 to the 16 times 17 to the 4 times 17 to the 1. Right? So if I figure out what each of these things individually are congruent to mod 5, right? Mod 5, then I can figure out what this is congruent to mod 5. Right? What that's congruent to. That's what I want to figure out. It's congruent to x mod 5. So like, let me just repeat that. So we're going to find what each of these things are congruent to mod 5 and then multiply all that together. And that's going to give us x here. It's going to be the product of all these things. Okay, so let's start. So I'm going to start with 17 to the 1, which is congruent to 2 mod 5, because it's 2 above a multiple of 5. Then we're going to move on to 17 squared, right? So 17 squared is an important property, is congruent to 2 squared mod 5, right? So I square both sides. That's not actually even a property I have listed, but I think that's a property he just kind of snuck in here. Oh, never mind. It is a property I have listed. What am I talking about? I thought he was sneaking in something. No, he's not. So there you go. There's a property, right? So if I square both sides, it still is congruent. So now, like, I'll just keep going. So this is congruent to 2 squared. So we can just keep going. But I guess I'll write, you know, this means that 17 squared is congruent to 4 mod 5. So I'll keep going. 17 to the 4 is congruent to 4 squared mod 5, right? So this tells us that, I'll do like bullet points to show where we are. Right, so this tells us that 17 to the 4 is congruent to 16 mod 5. So we've now learned our first fact, right? Well, our first fact was this, actually. This was our first fact. 17 to the 1 is congruent to 2 mod 5. Now we learned our second fact. 17 to the 4 is congruent to 16 mod 5. Right? So we're filling in these numbers. I found a 4 here. Oh, sorry, a 2 here and a 16 here. Right? You could put a 1 there too, I guess. Yeah, you could put a 1 here. So I'll replace that with 1 mod 5. Because 16 is 1 off from a multiple of 5. So you can just put a 1 here instead. That works too. Okay. Next one is going to be 17 to the what? 17 to the do different color. 17 to the 8 is congruent to 16 squared mod 5. So 17 to the 8 is congruent to 16 squared is 256. Right?
I think everything after that is just 1, 1, 1.
Yeah, I think everything after that is just 1, 1, 1. Right? Yeah, that makes sense. Right? So this is congruent to 1 mod 5, right? And yeah, that is what's going to happen. But I mean, we'll just show it just to prove it. But yeah, I mean, it's going to be just a couple more. Oh no, it's going to be more than a couple more. 16, 13, whatever. We're not that far. So next is 17 to the 16 is congruent to 256 squared mod 5, right? So 17 to the 16 is congruent to 256 squared. So that's some huge number, which is congruent to 1 mod 5, right? It's 1 off of a multiple of 5, right? Oh, they said to use some property here. Use the property that, that 17 squared is congruent to -1 mod 5. Maybe that makes it easier somehow. I don't know. It's true. It's 17 squared is congruent to 4, which is the same thing as -1. Oh yeah, okay, if you do that, okay, I see how that's going to make things easier. Okay, let's use that. Nothing's wrong with how I'm doing it. Nothing's wrong with how I'm doing it. But let's actually use that. Because it says, use the fact that 17 squared is congruent to -1 mod 5. Right? 17 squared is congruent to -1 mod 5. It's true because it's congruent to 4. So being 4 above a multiple of 5 is the same thing as being 1 below a multiple of 5. And now if I keep doing this process, it's much more clear that it's just going to be 1s the whole time. Because I'm going to get 17 to the 4 is congruent to -1 squared mod 5, which tells us that 17 to the 4 is congruent to 1 mod 5. Right? And then I'm just going to square it again and again and again and again. I'm going to keep squaring it. It's just going to be 1s the whole time. Right? It's just going to be 1s over and over again. Dot, dot, dot. So this tells us that when I do this decomposition here like this, right, it's a 2 here, and then a 1, then a 1, then a 1, then a 1. So the product of all these things, x equals 2. And so we get that 17 to the 213 is congruent to 2 mod 5. Can I type that into my calculator? Probably not. 17, no way. 213, yeah, math error. Just thought I'd try it. Just thought I'd try my luck. But anyways, there we go. That is our congruence question there with, breaking things up with the exponents like that. It's kind of definitely a tricky question. But yeah, if you didn't do this property where it's like -1s, like, use the -1 thing and square it, and you get 1s after that, you get the same answer. We'd get 1s every time here anyways, right? Because you just keep doing the congruence, but it's okay. And then if you even forgot to, convert, like here I got 256 as this one, right? And I said, oh, that's the same thing as 1. But even if you forgot to do that, you'd get some huge number here, but it'd still be true. It would just not be the smallest of the possible answers, but it'd still be true. And you could probably then note that it's congruent to 2, and then that'd be fine. That'd be the same thing. Okay. So there we go. That is our congruence example. I have a couple more. That's interesting. For example, here's an example here. It's kind of a cool one. 108 factorial is congruent to x mod 83. What do you guys think? No calculations needed for this one, by the way. What do you think? You can get this one. You can get this one without no, like, I can just write the x equals something. Yeah, Caleb's got it. X equals 0. Right? For sure. So the reason is because 108 factorial is equal to, a bunch of stuff times 83 times a bunch of stuff times 2 times 1. Right, okay, I'll say, 108 times 107 times ... times 83. So you can just think of it like, oh, that's some multiple of 83. It's definitely a multiple of 83, right? So we have that is congruent to 0 because 108 factorial is definitely going to be a multiple of 83. So that was a cool question. I saw it online. So, right. Yeah, it was pretty cool. So that's a good question. Yeah. So, and then another one here, kind of similar to what we just did, like before this one, 60 to the 59 mod 61. Sorry, mod 61. It's congruent to x. Mod 61. Right? So the way we do this one, not as easy. We just say, okay, well, 60 is congruent to -1 mod 61, right? It's 1 below a multiple of 61. So raising this to the 59th power, right? Well, we just get -1, right? So 60 to the 59 is congruent to -1 mod 61. Also kind of an interesting one, not as cool as this last one, but anyways. Also just a thing here to consider, if it's below, sometimes that's easier, especially if it's 1 below, because then you can say -1, and we have a good way of dealing with powers of -1, right? So we can deal with that there. Okay. Next one's actually my last congruence question. Before we last number theory question, before we move on to combinations, combinatorics. So find the inverse of 8 mod 11. So find the inverse of 8 mod 11, which means 8x congruent to 1 mod 11, right? Figure out what 1 is. Figure out what x is, I mean, right? It's kind of like the idea of an inverse, right? So like with multiplication, if we have like, 2 times x equals 1, then we define x as, 1 over 2, right? It's the multiplicative inverse. It's what gets you the identity, right? 1 is the identity element, right? So here we're doing the same thing. It's just that it's not multiplication. It's not going to be 1 over 8 now. It's going to be some other number that makes this product congruent to 1 mod 11. So let's figure it out. Wait, can you explain what the question is asking? It's asking solve this for x. Solve this equation for x. That's what like this equation right here. That's what the question is asking for. Solve this equation for x. Right. So that's what the inverse of 8 is. The x is like the definition of the inverse of 8 is x in this equation. It's what makes 8 congruent to 1 mod 11. Mod 11, because it gave us mod 11. So to do this, take some of my water. To do this, we actually break out the formal definition of congruence. So let me show you. Gotta break this guy out. Again, this is supposed to be n and then n here. So 8x congruent to 1 mod 11. That's the same thing as 11 divides 8x minus 1, right? Which is the same thing as 8x is equal to 1 plus k 11k, right? Plus 11k. So I'm just kind of breaking step by step. This is turning the congruence by definition into a division statement of a divide statement, and then this is breaking this up into what the divide statement means. It means that what it means is that 8x minus 1 is a multiple of 11, right? 8x minus 1 is a multiple of 11. It might actually make more sense to do it like this first. Let's just go with this, right? So the statement that this division thing is saying is, again, that 8x minus 1 is a multiple of 11. So this after a little bit of rearranging, is just a linear Diophantine equation, right? And we solve the linear Diophantine equation. We don't really care for y, call it k, but we don't really care for y. We just care what the x solutions are. And there will be infinite solutions. Will there be 0 or infinite solutions, right? Because remember, even this equation definitely has infinite solutions. There's infinite numbers you could put here that are congruent to 1 because it's in the cycle, right? It's in the whole cycle. And so one of those slices of that circle, mod 11, so there's 11 slices, there's an infinite number of numbers in that, infinite count of numbers in that slice. So they'll all be solutions here. So here, let's go ahead and do this. We have, first we have to figure out GCD, right? So GCD of 8 and 11, remember, make it positive, just make it positive. So 11 is equal to 1 times 8 plus 3. 8 is equal to 2 times 3 plus 2. 3 is equal to 1 times 2 plus 1. And 2 is equal to 1 times 2, or 2 times 1 plus 0. 1 is our GCD. GCD of 8 and 11 is 1. So definitely 1 divides 1, obviously. We do our LDE stuff to solve this now. So we rearrange this, first of all, for 1 equals 3 minus 1 times 2. Then we take this equation, rearrange it for the remainder. 8 minus 2 times 2 is equal to 8 minus 2 times 3. And then we substitute that in. So we get 1 equals 3 minus 1 times 8 minus 2 times 3. So it's substituting in for 2 here. I'm going too fast, let me know. I'll slow down. I'll explain it again if you want. And then, yeah.
I just kind of got confused with the 8 and the 11k part. This part is fine. This is just a simple GCD. But, okay, we're trying to turn the 11 divides 8x minus 1 into an equation.
Yeah.
As in like a Diophantine equation, essentially.
Yeah. Well, that's what it turns into for sure. That's definitely what it turns into here. Right? So this is just like, if I said that 2 divides 12, the reason for this is because 12 is a multiple of 2, right? In other words, 12 is equal to 2k for some k.
Yeah.
Right? So same thing here. If 11 divides 8x minus 1, that means 8x minus 1 is a multiple of 11.
Yeah, okay.
Right? And then I just rearrange that to an LDE, and then I solve it like an LDE.
Okay, makes sense. Thank you.
Okay, good. No problem. So carrying on, we substitute this in here. So we have 1 equals 3 minus 8, minus 1 times 8 plus 2 times 3. So we have 1 equals 3 times 3 minus 1 times 8. Okay, carrying on, we'll go to this equation here. Do it in a different color. We go to this equation here. We have 3 equals 11 minus 1 times 8. And we're going to substitute that in here. Or sorry, not there. We're going to substitute that in. Oh, forgive my arrows a little bit there. This is kind of bad, but it's okay. 1 equals, what did I just substitute? 3. So 3 times 11 minus 1 times 8. 11 minus 1 times 8 minus 1 times 8. So 1 equals 3 times 11 minus 3 times 8 minus 1 times 8. So we get 1 equals 3 times 11 minus 4 times 8. Yeah, that's fine. And then 1 equals, I'll just move it into the correct form. So 8 times negative 4 plus 11 times 3. And so that is our LDE here, right? Well, almost. So this was the LDE given to us. So x is definitely negative 4, right? And yeah, we don't actually even care for k, so it doesn't matter. But technically, so technically the solution here is x naught equals negative 4, and k naught equals negative 3. So you have to account for this negative sign by just making the solution negative 3, because then it's negative 3, right? But I won't write that because that's going to be confusing, so I'll put it there. We don't care about this k naught solution, though. We only care about x. So we got negative 4. So we 8, is that, did it say non-negative? Find the inverse. Yeah, as a linear combination of 8 and 11. Yeah, that doesn't really matter. Okay, it's fine. So, Yeah, that's fine. The solution, this was what we were trying to solve. Yeah, the hint is, I'll explain the hint in a second. The hint is kind of, it's useless. Like, it doesn't really matter. But, so here we get 8 times -4 congruent to 1 mod 11, right? So we get some negative number is congruent. This is definitely congruent to 1. That's fine as a solution. It's okay. Could you also do +4? Yeah. No, you can do +4. So, no, that's fine. There you go. Okay, the hint just wants you to figure out, GCD of 8 and 11 is 1. So write 1 as some combination of 8 and 11. So I guess you could say 24. 1 is equal to 32. You could do 48, 50. I don't know. Isn't it just saying that's how you're supposed to do it using Euclidean? Yeah, it's just sort of like, I don't know. I think it's just the way you're supposed to do it in your head by just figuring it out like that. But I guess so. Yeah. I guess it's implying to solve it as LDE. I don't really know. Yeah, I guess I thought I understood the hint. I think the hint is just trying to get you to do it kind of by inspection. But this totally works too. And there we go. So -4 is this. And then we have, that feels weird that's the answer.
Wait, can you explain the part where we find x0 and k0 again? Because like I know we're using the particular solution, right?
Yeah, we're only using the particular solution. We don't need any big, in fact, we don't even need the k0 part. We just need the x0 part. Right? Because that was the equation to begin with, right? We only care about the x. The k is arbitrary. It's like some k.
Wait, the original equation was 11, 8x, right? Oh, okay. Kind of confused about that, but
about what?
Like it says you said we're using the particular solution just to find x0 because k0 is arbitrary.
Yeah.
But how can that be if like we're using the particular solution?
Well, we're not. So I shouldn't have even said we're using the particular solution. We're not even using the particular solution. We're just using x0. That's it. Okay. We're just using x0. That's all we care about, because x0 is this from the original equation, right? The original equation was this. No k here. K doesn't matter, right? K only appeared here, but it's any number. K is just some number that we don't really care about, right?
Okay.
And so we just really want to solve for x. That's the whole point. This is solve for x. So we do it LDE, and then x0 is -4.
Oh, okay.
Okay. Yep, there you go. That's fine. That's the answer. We don't need to find a general solution for x now. It's fine. It just says find the inverse. So one inverse. You don't have to find all the inverses. I am recording, yes. Check, but it'd be a little bit late if I wasn't recording. I am recording. Why did I turn 3 into -3? It doesn't really matter for this question, but notice the equation itself has a negative sign, right? And we have a positive sign here. So just to account for that, I just made, it has to be negative to match the actual equation. So I just make it -3. Does that make sense? Yeah, okay. Okay, so I'm done with number theory then, guys. Let's move on to combinatorics. All right, so I'll just draw a little line. There we go. Come on, there we go. So combinatorics, I have a couple questions that we'll just go through. Starting off with some from another textbook, right? So here's one. This is from the discrete math textbook, for the Susanna Epp one. If you want access to it, you can message me after if you'd like. It's just another discrete math textbook. So the question here is, we have teams A and B are to play each other repeatedly until one wins 2 games in a row, or a total of 3 games. So one way in which this tournament can be played is for A to win the first game, B to win the second, and A to win the third and fourth game. So denote this by writing A, B, A, A. So how many ways can the tournament be played? Right? So the point of this question is just to show you this graph, pretty much. which is kind of the reason we have the, well, that's a horrible picture, just to show you the product rule, essentially, right? So here, let me write this here. Okay, so here we have like a branching tree of possibilities, right? So either, remember the rules for winning were A to win the first, one until you win 2 games in a row or a total of 3 games. So you start here, right? And we have, one possibility for the first step, right? Winner of game 1, right? So either A wins or B wins, and you branch that off into 2 parts here, right? And then from there, you branch again into 2 parts. So here, you end here, right? You keep branching off like this. And so this is kind of a way to show like a selection happening, right? A sort of like a selection happening here of how many ways you can end like this, right? So in this case, you can end in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ways. This has a little bit of a different, the criteria here of winning 2 games in a row is a little bit, the way the criteria is set up here is a little bit kind of different than how we do it in the class. But anyways, I just thought it was worth it to show you the branching tree. So I can show you another example for like, so if I have like another kind of similar thing where it's like, you take, let's just say something like this. You take 3 steps, or should I do like this? No, let's say like you are making a sandwich. Let's just do this, sandwich, right? So for step 1, for part 1, you choose your bread, right? You want a Subway sandwich. What kind of bread you get? You can get Italian. I can't spell Italian. You can, yeah, perfect. You can get a wrap, or you can get plain herbs, Italian herbs and cheese. Italian herbs and cheese. Okay, next one. You can get your protein. You can get tuna. I don't know. That's the first thing. Beef or cold cuts. There we go. Cold cuts. Okay. You can also get your sauce, right? Sauce. What's the sauce? You can get mayo. You can get chipotle, or you can get I don't know. You can get some other one. Mustard, right? Let's actually add an extra protein. Let's say, what else could you have? You could say chicken. There you go. Right, perfect. Yes. So the reason I'm doing this is because to show you the branching tree of this, right, would look like this. You can start with either getting, Italian bread, a wrap, or Italian herbs and cheese, right? So those are your 3 bread options, right? Breads. So this would be, so I'll just kind of color code it. So say Italian's the first one, wrap is the second one, Italian herb and cheese is the last one, right? Then you have 4 options branching off of all of these guys, right? Off of all of these guys. Now it's going to get impossible to draw immediately, but branching off of all of these guys, you have 4 options, right? One of these guys. Then, right, you have off of these ones 3 options, right, for the different sauces. So by the end of it, you have a whole lot of different ways you can combine the sandwich, right? So I can't draw all of them. It's gonna, it's gonna take a long time. But 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so you see we get a whole big branch with lots of different pathways you can take. But what we're interested in is how many of these final ones do we have, right? How many at the ends here do we have, right? So, well, think about it. Okay, how many of these do I have? For each one of these ends, right, I have 3, right? For each one of these choices, I have 3. 3 here, 3 here, 3 here, and 3 here, right? And for each one of these choices, right, I have, I have 4 choices, right? 4 choices, 4 choices, 4 choices, right? So essentially, like breaking off of this. And then to begin with, I have 3 choices. Just from the starting position, I have 3 choices. I can choose one of these 3, right? Choose one of these 3. And then from here, I have 4 choices, one of these 4. And then from here, I have 3 choices. So in total, you just want to take the product of it, right? Because it's just sort of like containers. Like this contains this contains 3 pathways. This contains 4 pathways, which each contain 3. So it's just a big product you're doing here. So the total answer at the end is going to be 3 times 4 times 3. And the reason I'm doing this is just because to show you, like, the product rule is just the product rule. You just multiply all the possible options, right? The amount of options in the first position, the amount of options in the second one, the amount of options in the third. But the reason is I think as branching tree is like a good way to visualize that. It's like why, right? Okay. Cool. Add Freddy food with franchise. Yes, for sure. Okay. So let's continue. Now we did a little diagram with this. Let's do some examples of using like the product rule. I think this is a good example. Did I by accident show the solution? No, I didn't show the solution. Okay, so we'll do kind of 2 variations of this, right? So I guess I showed the solution. I did show the solution. So well, too late now, but anyways. So a typical pin is a sequence of 4 symbols chosen from 26 letters and 10 digits, right? So we have 4 possible things. Repetitions allowed. How many different pins are possible? So we have 36 possibilities for here, 36 possibilities for here, 36 and 36, possibilities. These represent possibilities in each position. So you just take the product of all of them. And of course that's what the thing that I just showed here was, that I didn't mean to show. So there we go, right? So you see that, there's a bunch of steps. Each of those steps can be successfully like executed in one of 36 ways, and that number doesn't change, so we have that. But what if there was a slightly different, slight variation to the question, where now repetition's not allowed? So we form pins using 4 symbols, either letters of the alphabet or digits, and supposing the letters could be repeated. Now suppose that repetition's not allowed. How many different pins are there? So for the first option, we still have 4 positions, right? 1, 2, 3, 4. For the first option, we have 36 possibilities. But for the next one, we only have 35, right? Because repetition's not allowed, right? So we can't use a letter twice. And then for the next one, you have 34, and the next one, you have 33. So it's a slightly different product. That's the number here. 36 times 35 times 34 times 33. So 1,413,720. There we go. So just thought that was an interesting example because it shows, what happens if the numbers are changing every time, but they change in a way that makes sense, hopefully. Okay, so there's that one. Let's see what we've actually completed from this list here, all the way at the top here. So we've done all the congruent stuff. We've just done the product rule, so I'll just put that there, and then that there. So we got a couple more things to go through. So let's take a look next. What if the question was non-consecutive repetition? Yeah, let's take a look at that. So for non-consecutive repetition. So for the first option, you definitely have 36. Yeah, that makes sense. I understand what you mean. Yeah. So I'll just put here, what if it was only non-consecutive repetition, which is allowed, right? That's a question. So the first option definitely has 36, and the second option definitely has 35, right? Then I think the next one would still have 35, because you're not allowed to use this number, which certainly wasn't this number, but you are allowed to use this number now. So it's kind of like -1 + 1, and I think the next one will also be 35. That's my answer. I think so. I think that's right. Right? So there's 36 options for the first one. Here, right, we can't use this previous number, right? Here, we can't use this previous number, but we can use this number now, right? Here, we can't use this previous number, but we can use this number now, right? Or number or letter, whatever. So it's kind of like you're subtracting 1, adding 1 each time. So yeah.
So shouldn't that third one be 36? I'm confused.
Well, you can't use this number though, right? So you have one less. You have one option that you can't use. This last one, you mean?
Wait, no. Third one? Because okay, the question was out of 36 pin combinations, right?
Yeah,
or characters.
26 letters and 10 characters and 10 numbers.
Yeah. And essentially we're trying to find something that's non-consecutive. So the first one can be 36, which means just A, B, C, D, E all the way, and then 0 to 9, right?
Yes.
The next one can't have all of the previous.
Whatever the first
right?
one was. Whatever the first one was. Yeah. Can't have whatever this digit was.
So we have 35. But the second one can't have, the third one can't have the second one, but it can have the first.
Yeah.
So shouldn't the third one be 36 and not 35?
But it's still missing one. Like, it can't be this option, right? So it still has one option that it can't be. So there's 35 options then. Right? Whatever this digit was, this number cannot be that
one. Oh, okay. I think I get it. It's like
if this was A, then this cannot be A. It can be everything except A. So there's 35 options.
Yeah.
Yes, sir.
Yeah.
So essentially, it's like, okay, 36 is something, and 35 is A. Is 36 subtract A? Let's just say that.
Sure.
Right?
If this was A, then this is anything except A.
Yeah, and then the next one is anything.
Could be A. Could be A.
Yeah.
Could be A, but it can't be whatever this was.
Huh. Yikes! I hope I don't get this question because it's like it's a very deep conceptual question. It's like I don't know.
Sure. Yeah.
I don't know.
It's all right. Yeah, it definitely takes some time to think about. I think people who took grade 12 data management have a little leg up here because this has all been explained thoroughly before, right? But people who haven't taken that might be different. Okay, Ethan is saying something. So any position is allowed to have a character except 3 but not 2. Okay, let's see. Is there anything except for the previous character? If there are 36 possibilities, you're restricted in that you can't pick the previous option, meaning you have
I was just writing out what you were saying.
Yeah, okay, sounds good. I just want to read it and make sure, yeah. So if we're allowed to have 2 repetitions, do we have tools to solve that? Okay, what if we're allowed to have 2 repetitions, but not 3? Or 3 repetitions, yeah, 3 repetitions.
Like you can have the same character appearing like 3 times,
but not AAA.
2 times. Yeah, but you can't have AAA.
Okay, so there's 36 for the first position. There's also 36 for the second one. There's 35 for this one. Oops, 35 for this one. And then there's I don't know if I know what the next one's going to be here. If these first 3 are right. These first 3 are right. 36 again, you think? So if this was no, this is whatever, F. Yeah, what if this was AFF? This couldn't be an F. Right? So it can't be 36. Right? See what I mean? So not 36. Right? Does that make sense why this couldn't, like, this would, you're not allowed to be an F here, so there's a restriction. Oh, no, but this is any number. This is, yeah, that's fine. This, oh no, but this could be A. This could be A. There is 36 options here too. No, I think it's more complicated. I think this one's getting more complicated. But the third is only 35 if the first 2 reappear. Yeah, it's only 35 if the first 2 reappear. So you're kind of splitting into paths at this point. Yeah, repeat, yeah. Reappear, repeat. Yeah. I don't know the answer to this one. I'll think about it. I don't know the answer to this one. I'll write it here, you know. What if we allow double repetition but not triple? I don't know. No, we don't need to worry about it now. It's a good question, but I'm sure we're not going to get a question like that. Okay. It is an interesting question for sure. Yeah. Okay, let's take a look at principal inclusion exclusion 1. And then I think we'll move on to some
this was what again? Combinatorics?
We're in combinatorics now.
Yeah.
So
we're doing product rule. Okay.
That was product rule for sure. Yeah. Okay, so let's take a look here at these 2. This is from the textbook. Sorry, I have to restart OneNote again. Okay, so here, principal inclusion exclusion, determine the number of binary strings of length 10 that start with 101 or end with 00. So let's look at length 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're looking at the number of binary strings that start or end with 101. So 101, sorry, start, that's not what I meant to say. But number of binary strings that either start with 101 or end in 00, right? So the way we're going to do this is we're going to figure out how many start with 101, right? How many end with 00, and the principle of inclusion exclusion tells us that we have to subtract the ones that have both. Okay? Because they're being double counted. They're being counted here and here. So we have to subtract the ones that have both. Again, because they're being double counted. What is the difference between the product rule and the factorial equation for combinations? Well, the factorial rule for combinations, like NCR is equal to n factorial over n minus r factorial r factorial. I'm assuming this is what you mean. So this is not the same thing as number of. So yeah, okay. Could you solve this question up here with the same logic? I mean, you have 36. Yeah, 36. 36. Yeah, you could say 36 choose 1 times 36 choose 1 times 36 choose 1 times 36 choose 1. You see, this is telling you the number of ways that you can pick out 1 from 36, right? That's what this combinations thing is. We already know logically that the number of ways you can pick out something from 36 is there's 36 ways. Pick out a single thing from 36, there's 36 ways, right? But so multiplying them is a separate, that's the product rule. The fact that you're multiplying those things together is telling you that you're doing a bunch of steps in sequence. That's what it is. This is telling you the amount of ways you can complete the step. This is telling you that you're completing these steps in sequence. Does that make sense? The product rule is how you deal with the sequence, right? And then this is the combinations formula is telling you how many ways you can complete that step. Now we know it's 36 for this one, but yeah. Okay. So here, how many binary strings that start with 101? Well, you have one option for the first one option for the second one option for the third one, 2, 2, 2, 2, 2, 2, 2, right? That's how many options we have for all the rest of them. There's only one for the first three. It has to be 1 and 1, 1, 0, and then 1. So this is 2 to the 7. Yeah, and this is 2 to the 8. And then the number of binary strings that have both is 2 to the 5. And so the number, to answer the question here, how many binary strings start with 101 or end with 00? So the answer is going to be 2 to the 7 plus 2 to the 8 minus 2 to the 5. This is the principle of inclusion exclusion, which is saying that if I'm double counting, right? I'm double counting here, right? So I have to subtract off what I'm double counting. And there we go. That's your principle of inclusion exclusion. I'll write it here again. You have 2 options, 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 1 option, 1 option, 1 option, 1 option, 1 option, 1 option, 2, 2, 2, 2, 2. Okay. Let's look at this one. So this is 4.10, very similar question, right? So use the principle of inclusion exclusion to determine the number of binary strings of length 10 that start with 101 or end with 00 or have 1 1 at position 5 and 6. So we have 3 ors here, right? 3, 4, 5, 6, 10. So they start with 101 or end in 00, right? Or end in 00. Or have something in position, in position 5, 6, they have 1 1. So 1, 2, 3, 4, 5, 6. So 1 1. And so then we have to subtract off all the ones that are being double counted. So for example, well, let's just start with these numbers here. So how many possibilities for this? There's 2 to the 7, 2 to the 8, and 2 to the 8 here. So if anybody has trouble why I did that, then let me know. But it's just the number of blank spots. There's 2 options for each spot. But now we have to start subtracting off the things that we're double counting. So for example, what about the ones that have 101 and then also 00? How many of those? Well, there's 2 to the 5 of these guys. So we're going to subtract off 2 to the 5. But what about the ones that start with 101? Start with 101 and also have 1 in the 5, 6 position, right? Well, there's also 2 to the 5 here, right? So we're also going to subtract this off because these are being double counted. Right? And then finally, what about the ones that have 1 in the 5, 6 position and end in 0, 0? Okay, well, there's 2 to the 6 of these guys. But what about something that has all 3? This has been removed from the set, right? If it has all 3, we've removed this one too many times, right? Because we removed it twice here, removed this twice, and removed it twice here. So we removed 101, 101, 11, 11, 0, 0, 0, 0. We removed it twice. So we got to add this back. We took this away. We got to add this back. So there's 2 to the 3 options here. 2 to the 3 options here. So the total for this one is 2 to the 7 plus 2 to the 8 plus 2 to the 8 minus 2 to the 5 minus 2 to the 5 minus 2 to the 6 plus 2 to the 3. Not negative 6, but minus that. Right? So you add all the magnitudes, the magnitudes of the sets, right? You see the red but are being added. Sure, these are green. So these are the magnitudes of the sets. Then we subtract off all the unions, and then we add the triple union, right? So we're essentially doing principal, inclusion, exclusion. Let me find it. Where did I put it? Is it here's principle of inclusion, exclusion. So we're finding the magnitude of the union of all these sets, right? The set of all binary strings that start with 101, the set of all binary strings that end in 00, 0, and the set of all binary strings that have 1, 1 in the 5, 6 position. So the way we do this is we start by adding all the magnitudes together. Then we subtract off all the unions. And then we add all the triple intersections, but there's only one triple intersection. I think I said union by accident before, so let me repeat this. We start with adding together all the actual sizes of each set. Then we subtract off the intersections, the double intersections. And then we subtract off the triple intersections, but we only have one triple intersection. We have 3 sets, so there's only one triple intersection. Then we stop there. And if you had 4 sets, then you'd have a few more triple intersections. And then you would, subtract off the quadruple intersection. You keep just alternating this. If you're adding or subtracting, and here you're adding. Yeah, go ahead.
Oh, I know. I think at some point I started hearing subtracting when I'm supposed to hear adding, and I'm just got confused. But okay. The formula makes it good. It's just like it's almost like Pascal in a way with the negatives, but not really.
Sure. Yeah. So, it also helps because like Pascal, like binomial powers, like that thing. Yeah. Sure. Yeah. Similar to that, but different. But yeah. So he wrote it in class as -1 to the 2n or something like that, or -1 to the n. But
okay.
You just write it as you're just alternating the negative signs. So it's just you're adding all the magnitudes and subtracting all the double intersections, and adding all the triple intersections, then subtracting the quadruples, adding the quintuples. So you just keep going like that. And then, yeah. Okay. So hopefully that answers that, how that works. in the last 10 minutes, I think let's do a example. Oh, this example might be useful. Okay, let's do this quick example. How many pairs of distinct integers chosen from the set 1 to 101 have an even sum? So remember that for two numbers to have an even sum, right, it has to be, well, so even plus even is an even, right? Odd plus odd is also even. Every other combination is odd. Yeah, every other combination is odd. So we have to, pretty much figure out, how many are of a certain parity, right? So the parity is the even or odd. So the way we do this is we say, okay, how many odd numbers? Let's start with this. How many odd numbers? Hold on. Is this right? Even plus even is even. Odd plus odd is even. Odd plus even would be odd.
Odd.
Even plus odd.
Yeah, the other two are just
odd.
The same.
Yeah. So from here, we have that. Okay, I need to figure out how many odd numbers. Let me write that nicer. How many odd numbers are there? 1 to 101. So the way you do this is there's a formula for it. So it's the ceiling of 101 over 2. You can imagine if this was n, you just replace n there. So that's the formula for the number of odd numbers between 1 and 101. Okay? So 101 divided by 2 is 50.5. The ceiling of that is 51. So there are 51 odd numbers between 1 and 101. So we're going to think about this like making two choices here, right? Hold on. 50 over 2. Oh, yeah, okay, that makes sense. Never mind. So we can either choose two evens or choose two odds, right? That's our options. From the 100, so, from 101, from 101. That's our options. We can either choose two evens or choose two odds. So how many evens do we have? Well, there's 101 numbers in total. That means there's 51 odds. So there's 50 evens, choose two, or 51, choose two. And this is just a direct analog, right? Sorry, I should be clear. Not from 51. From 50 evens, from 51 odds, right? Choose two. There we go. That's more accurate. It's there. That turns into a plus sign, or it's a plus sign. That's like the summation roller. What's the word they used? Sum rule. There we go. A little bit of a weird question. When I tried this question, we had some trouble. Like the answer makes sense to me. This answer makes sense to me, but coming to it, I had a little trouble getting to the answer. But it's okay. I mean, I can explain it now. So that's kind of the idea. You can either pick from 50 evens, you can pick two evens, or from 51 odds, you can pick two odds. And there's the two different ways to do that. Let's see. 50 choose 2 is 1,225 plus 51 choose 2 is 1,275. Yeah. So 50 times 51, yeah, plus 50 times 49. So 5,000. Yeah, you're exactly two times as big. I honestly, yeah. So Ethan, you're doing the same thing that I did when I was trying to figure this out. And I couldn't really figure out why I was getting twice as big. Yeah, because NC2, n times n minus 1 over 2. let's talk about it after. If you want to talk about it after, like to figure it out. Like hopefully this answer makes sense. I think this answer is satisfying enough for me. Like I could come up with this answer, I think, on a test. Now, but definitely there is some way to do it how you're describing it, Ethan, and how Henad, Henad, you got it, but I don't know how I'd get to it exactly like that. So anyways, let's talk about that after for sure. The reason I say that is because I want to get to one binomial power question. Let's just do one quickly, and then we can finish up for today. Which one do you think I should do? Probably 6. Do 6. Let's just go right for the hardest one. This is actually a question I wrote. I teach grade 11 a lot, so I write some documents for grade 11 students that I teach, and so this was one of them. And so here we go. This is a practice question that I wrote. So we'll go ahead and do this. So 4y cubed minus 3x to the 5 to the 4. How do we expand this? That's the question, right? Expand this into something. Well, we draw Pascal's triangle, right? 3, 3, 1, 1, 4, 6, 4, 1. So we go to the 4th row. Right? We go to the 4th row. The 4th row because it's power 4. So we start by writing out these coefficients. 1, 4, 6, 4, 1. Leaving lots of space on purpose. Then this is our A, this is our B. So I write A, B as a product a bunch of times. So 4y cubed negative 3x to the 5 plus 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 4y cubed negative 3x to the 5. Okay, wrote it a bunch of times. Now, the power starts out as 4 for the A term. It starts as 4 up here and goes down by 1 each time. 4, 3, 2, 1, 0. And it is the opposite for the B term. 0, 1, 2, 3, 4. Now, powers of 0 are, of course, 1, right? And now let's just simplify. That's it. So this is just a way, those steps I described, I did a little bit fast, so maybe I can repeat the steps after. But it's just a way to get around using the actual summation formula, right? Which is what you're doing, but it's better to just remember the pattern. The pattern is not that complicated, right? So the coefficients are Pascal's triangle. You write A, B, A, B, A, B, A, B, A, B. Powers go 4, 3, 2, 1, 0 for the A term, and they go 0, 1, 2, 3, 4 for the B term. That's it. So this is going to be 4 to the 4, y to the 12, plus 4 to the 4, y to the 9, minus 3, x to the 5, plus 6, 4 squared, y to the 5, negative 3 squared, x to the 10, plus 4 squared, y cubed, negative 3 cubed, x to the 15, plus negative 3 to the 4, x to the 20. So 4 to the 4 is something, I don't know. 256. So y to the 12. So 256 times negative 3. Negative 768. That's y to the 9. I'll do x to the 5, y to the 9. Then here we have 6 times 16 times 9 is the coefficient. So 8, 6, 4, x to the 10, y to the 5. Then we have 16 times 9 times negative 3, negative 432 x to the 15 y cubed plus 3 times 3 times 3 times 3, 81 x to the 20. And that's as simplified as you can make. You can factor out a 2, I guess. No, you can't factor out a 2, so never mind. Okay, there you go. That's it. So we have expanded this original thing by, breaking it up into a whole bunch of terms here, using kind of this method here. This is the actual summation, the actual like notated summation. And then here it's just simplifying. It's just a long list of simplifying.
Wait, what was this question solving? Just to expand?
Expand this. The question was expand this.
And this was on the what topic then?
This is binomial powers.
Fun stuff. Okay.
Binomial.
This is literally. I mean, I don't really see how different it is from what I said earlier, which is like Pascal, triangle. Like you used it right here.
I used it. Yeah.
Yeah.
Exactly.
Huh. Okay.
So that's to get these numbers.
Fun stuff.
Just to get these numbers here, right? And yeah, we have this like this. In case anybody's confused about how to draw Pascal's triangle, maybe it's been a while since you've done it. I don't know if you can remember if Bonato explained it. You know, you just take the reason how I drew it so fast was just you just take the sum, right? 1 + 1 is 2. So 1 + 2 is 3. + 2 is 3. 4, 6, 4, 1. 3 + 1 is 4. 3 + 3 is 6. You just keep going like that. Anyways, so we go to the fourth row. Fourth row to get the n value is 4 here. Okay, guys. Well, I wanted to just do one, question like that. If you guys have any questions for me, I'm happy to answer. Otherwise, that's all the questions that I'll cover for today. But yeah, I'm here to stick around if you guys have any particular questions you want to ask me. I'm happy to answer the questions then. So yeah, let me know. But if you're gonna get going, thank you guys for joining. I hope the test goes well. Yeah, it's good. So why couldn't we do that for the previous question? Yeah, go ahead.
Oh, are you answering Ethan's question or mine? Sorry.
You can go. Joshua. You can go ahead. It's fine.
Yeah, I didn't understand the 101 even and odd question in the sense that how did you find that it was 100 and it was 51 odds and 50 evens? Is it just because you did 101 divided by 2, you would have gotten 50.5?
Yeah.
So
that's here. That's the section here, right?
Yeah. And then, so the question we're trying to find is how many pairs. Can I see the question again? How many pairs of distinct integers have even sums? Okay, meaning that we're adding 2 of these odd or even numbers together, and if they're even, okay, and then we solved it by doing NCR. Can you choose that?
Yeah, NCR, right? How many ways can you choose 2 numbers from a set of 50? That's exactly what this is describing. How many ways can you choose 2 numbers from a set of 50?
Okay.
Right? That's exactly what this notation means. So we have a set of 50 even numbers, and we want to choose 2 of them. Right?
Yeah.
And then add that to the amount of ways you can choose 50, choose 2 items from a set of 51. So we have 51 odds, we can choose 2 of them.
And then wait, so okay, yeah, because either one would give you even numbers, a sum of even numbers. Okay, I understand it now.
Yeah, either one will give you some even numbers. That's it.
All right, thanks, man. That's
no problem. Usual. No problem. Happy to help, Joshua.
I had no idea that you were doing this for test 1 and 2. It was just by coincidence. I was just like, man, I didn't
really?
get the pings, man. Yeah, so it's good though.
Because you're not in electrical computer. You're a unique one. You're a unique one.
I'm a very interesting fella sometimes.
Yes, that's true. That's true.
Well, thanks, man. And
yes, of course.
All the best with the final.
Of course. Good luck. Hope everything goes well.
Yeah, take care.
Okay, so Ethan, why can't we do this? Yes, good luck. Good luck. Hope everything goes well. Honestly, I don't really have a good answer because like my the way I looked at it. See if we can figure it out together. The way I looked at it when I originally approached this question, I said, okay, we're choosing 2 numbers, right? We're choosing 2 numbers. So from the first option, we can choose either, so we're choosing 2 numbers. It's either going to be 51, well, hold on. Now I'm confused. Now I'm confusing myself again. For the first option, so the first option, we have how many choices? Yeah, no. There's some issue with like an if statement in this. That's the thing. There's an issue with like if statement. Ethan, you're gonna say something?
Yeah, well, what I was gonna say is like if we assume the 2 different cases where both are odd or both are even, right? so that was my thought process of from a bank of 51 total odd numbers, we can do 51 times 50 because we're taking one and then we can't take that same number. And then 51 times 50 is how many odd pairs there are, plus 50 times 49 using the same logic for how many even pairs there are.
But the thing, but why can't you choose the same number again? If you choose 2, you can choose 2 plus 2 is even.
But if that's part of the question.
Oh, is distinct?
Yeah.
Distinct integers. Okay. So yeah, so you can choose 50. So for the even numbers, there's 50 even numbers for the first one, and the second choice would be 51, right?
For
so
the
that's,
even one?
That's for the 49. I mean, so yeah. you would have. That's how many ways you can choose 2 distinct even numbers. From a set of 50 even numbers. Yeah. That makes sense.
Mm-hmm.
Or you have 51 odd numbers, and there's 50, and you 50 for the second one. This does make sense what you're saying. This is how I did it too. This is exactly how I did it too when I was approaching the question. And I did convince myself that there was something wrong with it, but now I have to remember what was wrong with it. So obviously this isn't the answer, right? You get repetitions. So how would you alleviate like 2 plus 4? But 2 plus 4, that would be choosing.
Ooh, that's true. What Hanan said.
Oh, 2 plus 4 and 4 plus 2? And that's counted.
Because that's those are both distinct numbers, but it's not a distinct pair.
Oh.
Right? 2 is distinct from 4, and 4 is distinct from 2, but 2 and 4 is not distinct from 4 and 2.
Yeah.
So then you just divide by 2. I think, is that what you're saying, Hanan?
Okay, the step of that means we divide by 2 doesn't quite make sense to me. Like, I believe it. It is true. You do just divide by 2. I have to think about this one more, honestly. I don't know. I have to think about this one more. I know this is the answer, and this makes sense to me as to how we got that answer that way. But yeah, this is how I approached it as well. And there is an issue with you.
Okay. I think I understand then. Thank you.
Yeah, no problem. Okay, guys, I'm happy to answer any last questions before we get going. Otherwise, I will finish up for today. Good luck tomorrow. Hope everything goes well. No problem, guys. All right, I will stop recording. Stop recording here.